A particle with mass m is traveling in the xy plane and it has a position r and a velocity v. That particle is then going to have a momentum vector p that is going to point in the same direction as the velocity. The velocity and momentum vectors will always be parallel. And whatever this location is, there's going to be an angle phi here between the radial line from the position vector indicating the position of the object and the direction of the momentum. Here p is the linear momentum that we have seen previously. The equation for linear momentum is m times v, the mass times the velocity, and that's a vector quantity. If the particle has a momentum p, then it's also going to have an angular momentum relative to the origin. That angular momentum we represent with a capital L for no good reason other than we've used all the other variables, and we're going to define L thusly. L is the cross product of r cross p. This is r, the position vector of the object, and p, the linear momentum of the object. We have seen previously that the cross product of two vectors is going to be the product of the magnitudes of those two vectors, right? mv is the linear momentum p, and we're multiplying the two magnitudes of the vector by the sine of the angle between the two vectors. In this case, this angle phi, or if we pick up the momentum vector and place it at the origin, we'd have this angle phi over here as well. This is the magnitude, the amount of the angular momentum. When we take a cross product, the outcome is itself a vector. The direction of that vector is perpendicular to the plane containing both other vectors. It's perpendicular to both other vectors. So in this case, L is perpendicular to both r and p. Since r and p are both in the xy plane, L is going to be perpendicular to the xy plane, which means that L is along the z-axis.